What folks, y'all doing okay? Did y'all not want to come just like me this morning?
Oh, yesterday.
Oh, that was yesterday.
Yeah.
What's that day?
That was yesterday.
Okay. Oh,
Typically, it was
what did you have yesterday?
rain was running through the library.
Oh, right. Right. Yeah, we set out on the porch at lunchtime and saw all the students trying to make it through the blind. A lot of them just took their shoes off. Yeah, that's a good idea. Hey, listen, I wanted to show you something on the website I put up this morning. If you go there, you can find this grade calculator. I know we're sort of getting close to the end of the semester. Y'all are all anxious about what you want to get for your grade. If you open this, it's just an Excel spreadsheet that has all the things that we've had. So we've had exams 1, 2, and 3, and we're still to have exam 4. Let me zoom in a little bit so you can see. So these are exams 1 through 4, and then the final, which is to come. Your class participation, which, as I said, I forget where y'all were. I think you were right around 40 points at the last exam. That was sort of the average or the median, and that's sort of where you should be. So if you were at that point, or maybe a little below, a little above, you should have no trouble getting a 50 by the end of the semester. Right? So don't sweat that, especially if you're there. Also, the extra credit. So far, we've only had 15 points. There'll be a maximum of 20. I'm going to give you an assessment later in the semester or in the next week or so. That assessment will be over topics that we've covered in the class. It's really no need to prepare for it. It's just a general education assessment. We're required to give these assessments in this class. We took one last semester. Do you remember that? Similar to that, but on electricity and magnetism. That'll be worth 5 points, but it'll be a percentage. So depending on how you do on it, will be the amount of credit that you get. And it's usually students for about, 50% or so. So I wouldn't expect those full 5 points, but maybe 2 or 3 points you could pick up off of that. And then this calculates your average. So, this student, this isn't a real student, by the way. This student has these grades on their 4 exams. That's 100 out of 150, which is a 68%. They got 50 on their class participation, and then 15 on their extra credit, and they get a 68, which is a D. But obviously, I don't want anybody to get a D. But those are the sort of numbers. So you can play. You can put in your grades for exams 1 through 3 that you already know. If you're doing well in your class participation, just go ahead and assume that you'll get the full 50. You all have 15 points extra credit now, but maybe add in a couple points there, and then you can play around with your final and your exam 4 to see what you'll get in your final grade. All right. So that's just sort of how the numbers fall out. There's a lot of opportunity for credit, so you can play around with those numbers if you like. You have any questions about that? How we calculate the grade? I think it's fairly clear. Is that right? Is it clear? Okay. All right. Just to get this, I just add up all those numbers and divide by 600. That's the total amount. All right. Let me just sort of recap what we've been doing and sort of introducing this new stuff. Talked about Faraday's experiments where he, moved a magnet inside the coil wire and that generated a current, or he observed that there was a current, and he found that if he moved the magnet faster, then he got a bigger current, and if he moved the magnet in opposite directions, then he got currents that were in opposite directions. And so he generated this, or he created this law, wrote this law, which said that the EMF is induced if I have a changing magnetic flux. Right. This is our magnetic flux. This is different from the field. It's not the same. We've seen flux before. We saw that with gravitational fields. We calculated the flux. And this flux is equal to the integral, or the surface integral, of B dot dA. Right. But usually our magnetic field is not changing with respect to the area, and so we just say that this is equal to B times the area. That's the magnetic flux. And actually, it's BA times cosine of theta because of this dot product here. Right, so I can change the magnetic flux in a couple different ways, as we talked about last time. I can change the magnitude of the magnetic field. I can change the area of the loop or whatever it is that's inside the magnetic field. Or I can change the angle between them. I can cause the loop to rotate. and then that will cause a change in my magnetic flux if I change any one of these three things, and that will induce an EMF, an electromotive force, or a voltage. We'll see later that it actually generates an electric field, which is the result of this EMF, or which results in this EMF. Let's see, we did an example where we had a changing EMF, where I had one solenoid inside of the other, and this first solenoid changes its current, and that causes a change in this flux, or causes a change rather in the magnetic field, which causes a change in the flux, which generates an electric field or an EMF inside of the other solenoid. We'll work through another couple of examples, and I'll have some homework problems hopefully for you by this afternoon. That I'll post them on the website for you, and I'll get solutions up for them as well. Those will help you for the test to know sort of what to expect for the test. I expect it to be pretty straightforward. Are you feeling okay with this material so far? Yeah? Okay, good. Let's see, last time we left off, we were looking at Lenz's Law. Lenz's Law helps you to determine the direction of the magnetic field. So, for example, here if I have a loop, now this loop is sort of like this, right, where it's a circle, it's coming out of the page. But I have this bar magnet that's going into it. The magnetic field of this magnet is in this direction, or if I draw my field lines, they come out of the north, they go into the south. And so I can represent the magnetic field as an arrow to the left. And because this magnetic field is increasing in this direction, the magnetic field that's generated in the loop is going to be opposing that. And that's Lenz's Law. They found this just through experimentation. And they find that the induced magnetic field is opposite the magnetic field that's generating that magnetic. If I only have one magnetic field, because it's changing, I'm inducing a current within this loop that's causing another magnetic field. All right? Now, if I pull this back, if I have, or rather if I have another, if I change the orientation of my magnet so that it's south to north, and in this case, this is going in this direction, like I'm causing this magnet to move into this loop, the magnetic field here is to the right, which is just the opposite of that one. So the magnetic field that's caused by this loop wire is going to be to the left. So remember Lenz's Law, that the induced current has a direction, that is the current in these loops has a direction such that the magnetic field due to the current opposes the change in the flux that induces the current. All right, so the magnetic field here on the left, generated by this current, is opposite the magnetic field here. Yes? Right. It's a little more complicated than that because it has to do with how the magnetic flux is changing. So let's imagine another scenario where I have my north-south magnet. And now instead of moving it towards the loop, I'm now moving this magnet away from the loop. Alright, so while my magnetic field is still in this direction for this, it is decreasing. It has a decreasing flux at the loop. Alright, so at this point over here, my magnetic flux is in this direction, but it's decreasing. Right? So whereas before, when I was moving this magnet towards the loop, my magnetic field was in this direction. In this case, my magnetic field that's generated by the loop is going to be in this direction. So this is the magnetic field that is induced by that current. Right? So in this case, my magnetic, or my current that generates this magnetic field will be, let's see, if I have a magnetic field to the left, it's going to be up in this direction and down in this direction, assuming that this is the part of the loop that comes out towards you, and this is the part of the loop that's out behind you. Now, similarly, if I have a south-north, if I have another loop here, I have my bar magnet has the south pole here, the north pole here. So I can imagine the magnetic field of this is in this direction. And let's say that the velocity of this magnet is in this direction. What is going to be the direction of the magnetic field that's generated by this coil of wire? Is it going to be to the left or to the right? Now remember before, when it was going towards, the magnetic field opposed this magnetic field, so it would be to the left. But now that it's going away, what is the direction of the magnetic field generated by this loop? To the right. Right. So this is the magnetic field, we'll call it BM of the magnet. This is the magnetic field that's generated by that current, DI. Okay, so what is the direction of this current? I'm imagining this loop that goes like this as I'm looking at it, where this is the outside, this is the side closest to you, this is the side furthest away from you. What is the direction of that current? Remember our right-hand rule, we have our fingers are going to wrap around. So on this side, which is the closest to you, is it going to be going up or down? What? Down, right. So I imagine my magnetic field comes out, and so on this side, it goes down, and it's up like that. So I'm going to have a current on this going down, and this is up. Remember, this is the side closest to you. Okay? It all has to do with whether our flux is increasing or decreasing. If our flux is increasing, the magnetic field that's generated by this will be opposite the direction of the magnetic field that's causing the flux to increase. Right? If it's decreasing, as it is in these scenarios, in this case I have decreasing flux. I have decreasing flux just simply because I'm pulling this bar magnet away. And so as I'm pulling it away, the magnetic flux that's going through this loop is going down. Right, because if I think about my magnetic fields, if I draw them, they look like this. As I pull that away, the magnetic flux in the loop gets smaller and smaller. I'm getting further away from the magnet, so the magnetic flux will change in that way. So there are the four scenarios that we have. Our magnets are oriented like this, with our north and our south poles. If it's going towards the magnet, the magnetic field generated here will be in this direction. If it's going away from the magnet, it's going to be in this direction that we're drawn here. There's four scenarios. Let's do a few clicker questions that sort of deal with this idea. All right, so is there an induced current in this circuit? If so, what is its direction? So what I have here is I have a magnetic field that is to the right, shown by the blue lines. And then I have a wire, and I have a metal bar, and it can move along that wire. This isn't a magnet, this is just a conductor. And it's moving in this direction with the velocity to the right. So first, is there an induced current in this circuit? And if so, what is its direction? Remember, to get an induced current, you have to have a change in the flux. And that flux is that B.dA. Doing pretty well so far. Do about 10 more seconds. Just guess if you're not sure. We'll stop at 135. 135.
Okay, good. Why is there no current induced in this loop?
Yeah, and also just because the magnetic field is not changing, yeah, it's also going in the same direction. But the magnetic field here is not changing, so there is no changing flux within this loop.
In this circuit. Okay, this is a little trickier. Here I have a square loop of copper wire, and it's being pulled through this region of magnetic field. I want you to rank in order from strongest to weakest the forces F1, 2, 3, and 4 that must be applied to keep the loop moving at constant speed. So in order to move it through this magnetic field, you have to apply these forces to it. I want you to rank them in order from strongest to weakest. So where is it required to have the strongest force, and where is it required to have the weakest force? Now, as it moves through this magnetic field, there will be a current generated within that loop of copper wire, and that current then will experience a force, right from last chapter where we saw if you have a current moving through a magnetic field, it generates a force. I want to know where is that force the greatest and where is it the least? Okay, not too great here. Now, where is there no force required at all to move this loop? F1, right, because there's no forces acting on it. Where else is there no force acting on it? F3. Why is there no force required at F3 in order to keep it moving constantly through this magnetic field? It's in a uniform field and it's not changing, right? Now, F2 and F4, on the other hand, notice that as it's moving through here, the magnetic field is changing because it's going from an area with zero magnetic field to an area with non-zero magnetic field. All right? So F1 and F3 are both going to have what force? Zero force, right? So that is going to give us our either 1 or 4, A or D, right? Because they can both give F1 is equal to F3, and also both give these as the smallest value, say it's 0. All right, so now we need to think about F2 and F4. What are how are those two related? How are F2 and F4 related to one another? Okay, good. I'm going to stop at 3 minutes. Very good. A is the right answer. F2 and F4, they're experiencing the same change in the magnetic field, so they're also going to experience the same force. Do you know how to make a witch itch? Take away the W. All right. All right, a current carrying wire is pulled away from a conducting loop in the direction shown. As the wire is moving, is there a clockwise current around the loop, a counterclockwise current, or no current at all? So as I'm pulling this wire away, this wire generates a magnetic field, and I'm pulling it away. And I want to know then that will induce a current in this loop, which will cause a magnetic field. I want to know what is the direction of that current that is caused by this changing magnetic field. First thing you want to ask yourself is what is the direction of the magnetic field due to this wire? It's going to be on the top part is into the page or out of the page? Into the page. Out of the page over here. I'm pulling it away. So does that mean that the magnetic field is increasing or decreasing at the point where the loop is? Decreasing, right? Because it's getting further and further away from that loop, and so it has a decreasing flux at that point. And now you want to ask yourself, by Lenz's law, then is the magnetic field where this loop is, or induced by this loop, is it going to be the same direction or the opposite direction of the magnetic field here? And then, when you find that out, ask yourself, what is the direction of that current that causes that magnetic field? So y'all are pretty evenly split. There, by the way, there is a current in the loop, so C is not the right answer. There is a current in this loop because I do have a changing magnetic field up here. That's going to generate a current in the loop, which will cause another magnetic field by the loop. So, what is going to be the direction of the magnetic field caused by this loop? Will it be into the page or out of the page? Now, remember when we had these loops before, when we're talking about it in this way, let's say I had a north-south magnet like this, and I'm moving it in this direction, the magnetic field of this was in this direction, and so the magnetic field that was induced by this loop, where it's experiencing a decreasing flux, was going to be in the same direction as the magnetic field due to the permanent magnet. We have a similar situation here, but we're not dealing with a permanent magnet. We have this magnetic field generated by this wire, this current wire. So at the point of the loop, what is the direction of the magnetic field? Into the page or out of the page? Into the page, right. So this is an identical scenario to here. I have a magnetic field that's to the left, but decreasing. The flux is decreasing at this point. And so the magnetic field here is going to be in the same direction as the decreasing flux of the magnetic field here. All right, so similarly here, I have a decreasing flux. So my magnetic field generated by this loop will be in that direction. So now we're going to ask ourselves, what is the direction of the current that causes this magnetic field? All right, so we do our right-hand rule. Imagine our fingers go, our thumb goes in the direction of the current, then our like this, then our current has to go left. Erase this. This is a little confusing. If I have a magnetic field here, what must be the current? Is it clockwise or counterclockwise? It has to be clockwise, right? So my current here is clockwise. So I imagine my fingers in the direction of the current, say right here, it goes into the page and then out of the page on the other side. So this loop then, which will have a magnetic field that is, oh wait, I'm sorry. No. I stepped back. Y'all were right before, actually. Sorry, I was leading you astray. I will have a magnetic field, rather, that is into the page here, but because it's a loop, it's actually going to be in this direction here. All right. Is that what y'all were thinking? Huh? Yeah, because that's the answer most of you are given. All right, so my current then will be in that direction, which is counterclockwise. I'm sorry. Y'all follow me on this? There's sort of a lot of steps you have to go through in order to get to these answers. But here our current will be counterclockwise because the magnetic field that I'm generating is going to be in the same direction as the magnetic field caused by this wire because it's a decreasing flux, and then that's going to be a counterclockwise current. Stop at 625. Looks like we're all on the right page. All right. All right, a conducting loop is halfway into a magnetic field. Suppose the magnetic field begins to increase rapidly in strength. What happens to the loop? Is the loop going to be pushed upward toward the top of the page, downward toward the bottom of the page? Loop is pulled to the left into the magnetic field, or loop is pushed to the right out of the magnetic field. So here I have an increasing B field. That increasing magnetic field would generate a magnetic field within the loop, which is caused by a current in the loop. When I get that current in the loop, I will experience a force due to this part that will cause the loop to be pushed in one direction or another. First of all, what is going to be the direction of my magnetic field? Here I have an increasing magnetic field. Remember, our flux is BA. So in this case, I'm increasing my magnetic field. That's increasing my flux. So here, what is going to be the direction of my magnetic field? It's going to be into the page or out of the page? What is it? It's going to be into the page. So the magnetic field that is induced by this loop is going to be out of the page. Let's say into the page. I'm sorry, out of the page. It's going to be opposite the magnetic field that's generated by this whatever is making this magnetic field. Is that one of us? Or is that outside? All right. So what then will happen to this loop that has this magnetic field being generated due to this change in flux? A lot of you have the right answer, but still a few of you do not.
What does everybody have?
Okay, what is the direction of the current that causes the red dots there? Is it clockwise or counterclockwise? Right, so I have a current in this loop that goes in this direction, counterclockwise. Now, I have a force that acts on each part of this loop. Let's just take this part. I don't need to consider these parts because I know they have forces that are equal and opposite because they have opposite currents, and so those forces aren't going to affect the loop at all. So now I want to ask myself the question is, what is the direction of the force on this section of wire that has a magnetic field in that direction, or excuse me, a current in that direction that sits inside of a magnetic field that is like that? What is the force that acts on that wire? It's to the right. Right, so remember my fingers in the direction of the current, they fold into the magnetic field, and so my force then is going to be to the right. All right, we're going to come back to this. We'll get to inductors today or tomorrow. Oh, I'm sorry, let's see, this was the... Okay, let's do an example. Let's say that I have a battery. It's hooked up to a loop of wire like this, and this loop of wire sits inside of a magnetic field. And that magnetic field is changing, and it changes by this function, 4t squared plus 2t plus 3. And this is the magnetic field. It's in Tesla. It's in units of Tesla. And it's in the, what's this, the positive k direction. Right, but the magnitude of it is given by this function, 4t squared plus 2t plus 3. Let's say that the resistance of this wire is equal to 2 ohms. Let's say that the EMF of this battery is 2 volts. And I want to know a couple things. At t equal 10 seconds, what is the induced EMF in the loop? All right, I have a couple things going on here. I have the EMF of the battery here, but in addition to that, because I have this coil of wire that sits inside of a changing magnetic field, I also have an EMF that's being generated in this. This is going to be important when we get into inductors because they operate much the same way. They have an induced EMF that changes. So at t equal 10 seconds, what is the induced EMF of the loop? Now, by Faraday's law, I know that E is equal to negative d phi dt. And that I also know that my magnetic flux is just equal to B times A. So E is equal to the negative of A dB dt, where A is the area. That's just going to be pi r squared times the derivative of that function. Now what is the derivative of this function here? Right, 8t plus 2. And that describes to us how the magnetic field changes. 8t plus 2. All right, I can find the area. Actually, this it's not pi r squared. It's going to actually be pi r squared over 2. Because I'm imagining here that I have this semicircle that has a radius r, and actually this part is not in the magnetic field. It's just a semicircle that is sitting in the magnetic field. So I can find the area of that. That's going to be negative pi. Let's just say the radius is 0.2 meters squared. I divide that by 2 just because it's a semicircle, times 8 times 10 plus 2. And then if I calculate that, I get my EMF. Let's just look for the magnitude of the EMF. It's going to be 5.2 volts. This negative here just means that the induced EMF, or the induced magnetic field, opposes the originating magnetic field. Which is what we've been talking about in Lenz's law, where my magnetic field that's caused by this coil opposes the magnetic field which is causing that magnetic field. Alright, so I have an induced EMF of 5.2 volts. So I can imagine that there's like another battery up here that has 5.2 volts. All right, so now I want to know is what is the direction of this EMF? Like, should I draw it as a battery like that, where it's the high and then the low potential, or should I have it switched, where I have it where I have the EMF going in the opposite direction? Y'all follow what I mean? Basically, I'm trying to ask, what is the direction of the what? The current, right. So I want to know what then is the direction of the current in this loop. So let me erase this battery, sort of clean this up a little bit. All right, so I want to know now, what is the direction of the magnetic field? What is the direction of the magnetic field that is caused by this loop of wire? Now the magnetic field here is out of the phase. So I know that the magnetic field that's generated by this loop of wire, that it's either going to be into the phase or out of the phase. And so the question I want to ask myself is whether the magnetic field, the blue dots here, if they're increasing or decreasing. If they're increasing, the magnetic field that's induced will be what? The same or an opposite direction? Opposite direction. That's Faraday's law. That's what that negative means in Faraday's law, that negative dq/dt. It means that my magnetic field will oppose the direction of my changing flux. So if this is an increasing magnetic field, my induced magnetic field will be opposite direction, into the phase. And vice versa. If this is a decreasing magnetic field, the direction will be the same direction, out of the phase. Which is it? Is it an increasing or decreasing magnetic field given by this function? It's an increasing magnetic field. At t equal 10 seconds, I can see that. Because remember, whether it's increasing or decreasing is given by the derivative, dB dt. And that's 4t squared plus 2. Or excuse me, not 4t squared, 8t plus 2. Right, and at t equal 10 seconds, this value is positive. So I know then that the magnetic field at t equal 10 seconds is negative. That might not be the case. It sort of depends on the function that you have and the time that you have it at. But in this case, my changing magnetic field has a value of 82. It changes at a rate of 82 Tesla per second at t equal 10 seconds. And that's how we find this through the derivative. It tells us how much it's changing at a given time. Okay, so I know then that the direction of the induced magnetic field is what? Into or out of the page? Into the page, right. So my induced magnetic field will look like this. Now, is the current here going to be clockwise or counterclockwise? Let's see, so my magnetic field, yeah, if I have a current that is in this direction, it gives me a magnetic field into the page and out of the page. So yeah, my current then is going to be flowing in this direction. All right, so my current, due to my induced EMF, goes in that direction. What is the direction of the current that's given by the battery? It's going to be the opposite. So my current here, remember current always flows off the positive terminal of the battery, is in that direction. So that means that I'm going to have a two opposing fields, right? So I have one EMF that is in one direction and another EMF that's in the opposite direction. So where I have 2 volts here and 5.2 volts here, my net EMF is going to be what? Right, so my net EMF will equal to 5.2 minus 2 volts, which is 3.2 volts. So if the next question is, what is the current? All right, and I know that my EMF is 3.2 volts, so that's just going to be 3.2 volts. V is equal to IR. My R was 2 ohms, so I is equal to 1.6 amps. If I want to look at the direction of that, the direction is going to be what? Is it going to be clockwise or counterclockwise in the loop, the direction of my current? Right, clockwise, because I have 5.2 volts here and that overwhelms the 2 volts. So I'm going to have a current of 1.6 amps that is going to be clockwise in that loop. So my, let's see, I drew it the other way. If I think about my circuit, it's going to look sort of like this. I can imagine another battery up here. This one's 5.2 volts, this one's 2 volts, and it's going to drive a current of 1.6 amps in this direction. Of course, there's not really a battery in this loop. This voltage is being induced by that changing magnetic field. Okay? All right. It's important for inductors. We're going to get into inductors, and it's actually pretty important for when we get into electromagnetic radiation, because electromagnetic radiation is a changing magnetic field, and that also generates a changing electric field. So we get these sort of 2 magnetic field and electric field that are both changing. Let's look at induced E fields. Can I go down from here? There's a homework problem that I'll send out later to help you practice this some more. All right, let's see, induced E fields. In these sections, as I've told you, sort of doing this new material, and there are no sort of other tests for you to practice off of, so your homework will be sort of your go-to, and your test questions will be very similar to your homework questions, okay? So practicing that homework will help you. They won't be exactly the same, but they'll be largely the same. If you can do the homework, you should be okay. Is that clear what I mean? Okay. All right, let's look at induced E fields. A changing magnetic field produces an electric field. And we see this in Faraday's law. You know, that is that the EMF is equal to negative d phi dt. That basically a change, Faraday's law says that you have this change in flux causes an EMF. But an EMF is simply caused by an electric field. So while we talk about batteries in terms of potential, really a battery is generating an electric field within your wire, and that's what's causing your electrons to move from one point to another because of this electric field. But we talk about it in terms of an electromotive force or in terms of potential, that they move from an area of either low or high potential to the other. But a changing magnetic field will actually generate an electric field. Now, so far we've assumed that we have some conductor through which these things are moving. So we have a coil of wire and a magnetic field. But you don't need a medium for current to flow in order to have an electric field. Let me draw a picture for you. All right, so let's say, can I go down, Neil? Let's say that we have a magnetic field that's like this. This is an increasing magnetic field, like we had before. Let's say that I have a loop inside of this, a loop of wire. The loop of wire is going to generate a magnetic field that will be opposite. Which means that I will have a current that flows in this direction. That will be my current. That current is causes the magnetic field by the blue dots, by our right-hand rule. All right. Now I can also imagine that I have not a current, but I also have an electric field. And this electric field is actually what causes this current. So I have this electric field that is actually causing this current. Right. But if I get rid of the wire completely, it's not like the current goes, or like the electric field goes away. So imagine instead, I just have this increasing magnetic field here. So the same magnetic field that's increasing. I'm still going to have electric field lines that will go in the same direction. So I have an electric field line there, an electric field line there, all around like that. I have this electric field that's due to the magnetic field that's changing. Right, so you don't have to have wires and all that jazz in order to have this electric field. You can have this electric field just in space. And this changing magnetic field, in this case, the red X's are an increasing magnetic field. And just like they cause a current to occur in this wire, they also cause this electric field to occur in space. We can write this. We're not going to see this again. Let me just write it because you might see it elsewhere if you get into Maxwell's equations and what have you. But the surface integral of E dot ds, it turns out this is my electric field. ds is my surface over which I'm integrating. Turns out that this is equal to our electromotive force, and so just by simply rewriting Faraday's law, I can have the integral of E dot ds then is equal to the negative d phi dt. So my changing flux causes my electric field. This is just a rewriting of Faraday's law. All right. We're going to get into some more practical stuff than this, but we'll see this again hopefully in the next chapter, if we have time to get to it, where we have this changing magnetic field that causes an electric field. And if you know electromagnetic waves, those are perpendicular electric and magnetic fields, and they come about through this. When I have this changing magnetic field, I also get a changing electric field. Let's look at inductors, though, and inductance. These are things that we have in a circuit. We'll look at LR circuits and also LRC circuits. They operate in practice a lot like capacitor circuits. The symbol looks like this. You might have seen it before if you look at circuit diagrams. It just looks like a coil of wire. In fact, it is a coil of wire. A lot of inductors are simply just a solenoid, which is just a coil of wire. The variable that we use for these is a capital L, and the unit that we use for inductance to describe these materials is a Henry, and 1 Henry is abbreviated 1H, and it's equal to 1 Tesla meter squared per amp. Basically, when I run a current through the solenoid, I generate a magnetic field, and the inductance then is equal to N times the magnetic flux divided by the current. Remember, this magnetic flux is equal to B and A. So the inductance is related to this magnetic field that's generated times the area. And our inductance is equal to N times phi over I. This, by the way, is called the flux linkage. We'll see that again later. All right. Yeah, Josh. Oh, N is the number of turns.
Oh.
So N is just, if I think about this as a solenoid, which it is basically, N is the number of turns. All right. We're going to move into RL circuits next time, but I'll wait. We'll just pick up that next time. You'll look like you're about to keel over. I know this isn't the most interesting of topics, is it? It's actually pretty interesting, but it's kind of dry right now. All right. We'll work through some more sample problems next time. I'll get those homework problems to you soon so you can be practicing. And I'll see you on Friday. Okay?